Okay, time to start. Time to start our second presentation for this breakout. And the second presentation will be offered by William Bayliss. William Bayliss worked in the field of language teaching and assessment for 10 years as teacher and then academic manager in Chinese private language schools before transitioning into the role of assessor and assessment trainer and now consultant. He's got a wealth of experience in team management, programming, and assessment delivery. And today he will be talking about investigating scale length and inter-rater reliability in auto-rater assessment. This, as you can see already on the screen. Again, to all of you, please, if you have any questions or comments, just type them in the chat box and I'll make sure to read them out at the end of the 20-minute presentation here. William, the floor is yours.
Thank you very much, Chris. Good afternoon, everyone, and welcome to my breakout session. For the past 2 years, my colleagues Trevor Breakspear, Jan Langerslag, and myself have been working with the IELTS partners on the IELTS Smart Learning ISL or ISL application. This AI-powered low-stakes assessment application aims to give fine-grained feedback to middle and high school students in China to help them improve their spoken English. Today's session will zoom in on the initial phase of developing a task for ISL, which taps into elements of the IELTS speaking test part 1 and part 2 constructs. For this task, we developed a mechanism to collect human ratings that will eventually train a machine rater. This iterative process involved a 13-band and a 7-band scale for rating, which produced some very interesting data. I saw this data as a rare opportunity to compare scale lengths. The analysis of this data is the focus of my talk today. The session will discuss the following research questions. Are there acceptable levels of inter-rater reliability for low-stakes auto-rated assessment? And how does inter-rater reliability in a 12-band or 13-band scale compare to a 7-band scale? To help frame what is to follow, it's important to be clear about what is meant by the terms low stakes and inter-rater reliability. Let's look at each of these in turn and then discuss scale length. Let's look at stakes, high and low first. According to these definitions from Bachman and Palmer, the key differences are those of the impact of decisions made and the ease with which these decisions can be reversed. So for high stakes decisions, there are major impacts and the decisions are not easily reversed, and the opposite is true for low stakes decisions, in that they are relatively minor impact and can generally be reversed quite easily. Regarding inter-rater reliability, here I've used a definition from Alderson, Clapham and Wall, where they say that inter-rater reliability is the degree of similarity between different examiners. Can 2 or more examiners, without influencing one another, give the same marks to the same set of scripts or performances? Through the lens of today's workshop and its research questions, these definitions of high and low stakes decisions and inter-rater reliability raise some questions. How do levels of rater scrutiny differ between a low stakes AI assessment app and other assessment types? What impact do these decisions made by the machine rater have on users of the app? How easily can the ISL machine rater decisions be reversed? And what steps did we take to maximize inter-rater reliability? Let's address the first 3 questions first. In short, the machine is only as good as its training data. Although the decisions made by ISL are low impact, the machine leveraged by the app has the potential to make a huge number of decisions for a huge number of students. Therefore, combined, these decisions will likely have relatively high impact on teachers, students, parents, curriculum, and schools. Although the individual decisions made by ISL can easily be reversed, long-term use of the app could lead to positive or negative washback For example, changes in the user's learning behavior, language use, and curriculum. These would be harder to reverse. The implications of these factors being that the performance of the engine is paramount, and this accounts for the higher than normal levels of scrutiny placed on the data and, by implication, the raters. Let's look at some strategies that we used to maximize the reliability of this data. There's an abundance of guidance in the literature for best practice that aim to improve inter-rater reliability. For example, Alderson, Clapham and Wall, and more recently, Knock, Fairburn and Gin. An in-depth discussion of this guidance is beyond the scope of this presentation. I would, however, highlight some key strategies employed that in some cases went well beyond the requirements for even high-stakes tests. Raters were divided into 6 teams of 3, and all recordings triple or more marked, and some were marked by the whole cohort. Our monitoring system sampled every rating for many facets rash analysis. This process continued throughout the project, allowing us to highlight problem areas to raters to help them improve. The scale's performance was monitored and revised as necessary. The raters were also retrained and re-standardized whenever it was deemed necessary to do so. Now let's talk about the scales that we used. Why attempt a 13-band scale? Well, the IELTS Smart Learning application is designed to measure progress over time and tease out small differences in performance. It needs granularity to deliver this. The chosen scale length came down to a compromise between what's reliable and the level of granularity. An analytic rather than holistic scale was also implemented, as these types of scale highlight more performance features to the raters. And it was decided that the payoff from a 13-band 5 criteria scale made it worth attempting, even though this goes against the received wisdom, summed up by Miller's dictum of 7 ± 2. Here's a mock-up of the scale that we used. Due to the confidential nature of the band descriptors, I can't share the full documents here today. As you can see from the slide, the even bands contained the rich descriptors of each level and criteria, and the odd bands existed as intermediates between those. Even bands contain some of the features of the above and the below. Why then did we reject 13 bands? On the slide, you can see the rationale provided by Trevor Breakspear, my colleague, for the ISIL academic team's decision to collapse the scale to 7 bands. Initial analysis indicated that internal consistency was too low to train our tech partner, iFlyTech's evaluation engine. The reason for this lower reliability may lie in the high cognitive load exerted on the raters by a 13-band 5 criteria scale. In short, the granularity is no use if the data is not reliable enough. What then did the 7-band scale look like? Well, as you can see, it was the same as the 13-band scale without the intermediate bands. Why did we do this? Well, firstly, we'd had success in a sister part of the ISIL product, the placement test, and we'd had success with 7 bands. As I said, collapsing the scale was simply a case of removing the intermediate bands, and the raters already had experience using the 13-band scale, so just removing the intermediate bands meant retraining for the new scale was minimal. Next, I'd like to talk about the data analysis I am going to talk you through today. As stated in my introduction, the data collected on both scale lengths is a rare opportunity to compare the scales. For this analysis, I selected the data that involves the fewest independent variables so that analysis would give the clearest possible indication of differences between a 7 and a 13-band scale. The initial batches used the 13-band scale. Batches 3 onwards used the 7-band scale. I only selected data for this analysis from batches 1 to 4, as I didn't want the 7-band scale analysis to have a lot more data than the 12-band analysis. This slide shows a table of all the data sets that were rated in batches 1 to 4 and by whom. The 4 colors represent samples where the data set, the prompt, and the IELTS part were all the same. So the pairs, yellow and orange, green and blue, differ only in scale length and data set, so are the strongest groupings for comparisons to be made. Because the IELTS test takers and prompts are different between groups 2 and 3 and 5 and 6, any comparisons need to be made with caution. The analysis I will share with you was run in multi-facet rash measurement using the Minifac software program. The rationale for this was that this type of analysis reveals rating patterns that other indices may not, and is also very powerful in the examination of rating scale function, as pointed out by Nock, Fairbairn and Jin. There are a lot more useful measures provided by rash analysis, but they're beyond the scope of today's presentation. The following slides first describe the results of the relatively crude agreement indices, exact agreement, and then much more nuanced probability curves. In terms of guidance from the literature regarding exact agreement, Nock, Fairbairn and Jin explain that although many textbooks set the acceptable levels of exact agreement at 80%, in reality, levels usually fall between 40 and 60. We can see then that the 13-band scale here falls well below this, but with so many bands, we would expect this number to be lower than with a shorter scale. For the 7-band scale, we can see that the levels of exact agreement are well within suggested tolerances. The next element of rash measurement requires some explanation. The important thing isn't to understand the minutiae of the mathematical model, it's to understand the implications regarding the scale. The probability curve is a graphical representation of the statistics produced by multi-facet rash measurement. Combined with various category statistics, scale performance can be analysed in detail, and that's what I want to do today. This slide shows a probability curve for a well-functioning 4-category rating scale. This comes from Bond and Fox. Let's break it down. The most important element of rash analysis is to understand what makes up the x-axis on this graph. Simply put, it represents a measuring stick for difficulty and ability. The scale of this measuring stick is in logits. This is essentially a clever mathematical way of making an equal interval ruler with a midpoint at. The type of analysis assumes that the difficulty of being awarded a band score correlates perfectly with the ability of the test taker. This means that we can reduce these two things into a single x-axis. The y-axis, on the other hand, demonstrates probability from 0 to 1 or 0 to 100%. Each individual number on this graph represents the probability of getting that score at that level of ability. So where the two lines intersect is the point where one score becomes less likely than the next. In this example, all 4 bands of the rating scale are discriminating well. So if we imagine a group of test takers, if you have the weakest test taker, that person would be at -4 on the x-axis. As we can see, and as we would expect, that person is most likely to get a band 1 score and unlikely to get a band 2 score. At the other end of the scale, if someone is a very able student, as you would imagine, they're very likely to get a 4, they're unlikely to get a 3. And if we look in the middle of the scale, a person of middle ability is equally likely to get a 2 or a 3. Now I'd like to talk about some category statistics. These are essentially a numerical way of describing what we can see graphically in the probability curves. I want to discuss three. The first is counts. In short, for each of the scale numbers, we need to have enough data to estimate them. If that number is less than 10, there's not enough data. Also, I'd like to talk about average measures. This is simply that we expect the band scores to go up in numerical order. 1, 2, 3, 4, 5, 6, 7, 8, 9, not 1, 2, 3, 5, 6, 9, 7, or whatever else. And then finally, threshold measures. Also, we expect these to progress in order, but we also want them to be evenly spaced. Just like on a ruler, we want our centimeters or inches to be the same size. It's the same with our rating scale. Here are the probability curves for batch 2. As we can see just by looking at the curves in comparison to Bond and Fox's ideal curves, we can see that the 13 band batches perform poorly with weak discrimination between the bands. In the table on the right and on the following slides, I have added a column I call threshold measure gap. This is simply the difference between the threshold measures of adjacent bands. So how big the centimeters on that ruler are. The counts of bands 2 and 11 are below the recommended threshold. As you will see, this is the case for all of the groups and batches analysed. In-depth discussion of this problem is beyond the scope of today's presentation. However, for those who are interested, I will be explaining our strategy for dealing with this problem in Trevor, Jan, and my presentation tomorrow afternoon. In terms of average measures, if we look at this column, we can see that they do not always increase in number order. The measure for band 3 is lower than the measure for band 2. However, if we look at the counts, we can see that band 2 doesn't have a high enough count for responses for an estimation of the threshold value. In terms of threshold measures, we can see that not all of them are in order, but more importantly, we can also see that the gap between the thresholds are below the accepted tolerance, except for one at band 4. These measures seem to indicate that there is less measurement precision with this 13 band scale and therefore a greater chance of inappropriate scoring. This is the part 2, so this is the second batch that included 13 bands. Again, counts at the extremes are below the suggested threshold. In terms of average measures, we can see that bands 10 and 11 are out of number order. Both bands in this case have counts above the threshold of 10. In terms of threshold measures, I think this is the most interesting data that I found in my analysis. Again, we can see that not all of the threshold measures are in number order. But more importantly, again, if we look at the threshold measure gap, we can see that the bands alternate between being inside and outside of the suggested thresholds. This suggests that either the rich descriptors or the intermediate bands are not functioning properly. This would be a very interesting line of further research. Now, if we compare these two probability curves with those for 7 bands, there is a distinct difference. As you can see, the distinctions between the bands are clear, and this suggests the scales are performing well. In terms of counts, again, we can see the extreme bands have low counts. Average measures increase in number order, and threshold measures increase in number order, and the gaps are within accepted tolerances. And finally, for the final probability curve, we can see that there are low counts at the very extremes. Again, they increase, the average measures increase in number order. And finally, for the threshold measure, they increase in number order and the gaps are within accepted tolerances, except for bands 2 and 3. Now, I don't know how to account for this. as the counts are well within suggested tolerances, so there's enough data to for calculation. Further investigation is needed. Going back then to my research questions. In terms of research question 1, I don't think it's possible to answer this question until the machine has been trained by the data and we validate its output. As I explained above, various strategies have been deployed to maximize reliability. In terms of question 2, in as far as scale function is concerned, the data suggests that a 7-band scale functions better than a 13-band scale. We would expect more reliable rating from raters using the shorter scale. So in conclusion, the claims made by the literature that point to longer scales having reduced reliability seem to be supported by this data. The data also supports the decision to collapse the scale from 13 to 7 bands. I think I agree with Nock, Fairbairn and Jin when they say there's no such thing as a perfect scale. There are always trade-offs. As many have pointed out, scale type should match the purpose of the assessment. Developing scales is very expensive. It's possible that a 13-band scale could have been made to work, or that a 9-band scale may have been a better compromise, but we didn't have the funds to explore this further. So what insights can this research give teachers and small-scale assessors? Well, teachers often create rating scales for various educational purposes. They need to decide how many levels of discrimination are needed. This study and the bulk of the literature suggests that the longer the scale and the more analytic criteria they have, then the process will be more resource intensive and it will be less reliable. A balance needs to be struck between the levels of reliability demanded and the granularity of the ratings. In short, be very clear about what you want to measure and make the rating scale and its criteria as simple as possible. Thank you very much. That's the end of my presentation.
Thank you very much, William. And now it's question and answer time. And I've already got one question from Catherine Hughes. The question, I'll read it. My understanding is that with a 13-band scale, raters were trained to award an odd score per criterion if candidates demonstrated proficiency higher or lower than the final score. For example, rater awards 9 if the test taker meets criteria band 8 and 10. When you collapse the scale to a 7-point scale, how did raters decide when to award bands in cases when proficiency was between bands? For example, when to award a band 5 or 6.
I would say that they did it in the same way that, say, an IELTS examiner would deal with. You have to make a judgment call about which scriptures you feel the performance fits best. And unfortunately, sometimes you will get the situation where it's very hard to choose between the two.
Okay. The next question is from Brenda Yuen, and she's asking, as category 6 doesn't have enough counts, 10 counts, in a 7-point scale, have you adjusted the level descriptors for category 6 to make this level more achievable?
Well, I think that there are two things going on. Firstly, usually, or from my understanding, the scores that any population of test takers get will tend towards a normal distribution, so you people at the ends. So it might be possible in the sample that I've shown that they're just those levels of ability. Also, there is a tendency, and we did see this tendency, for raters to to rate with central tendency. So rather than trying the extremes, they would rate in the middle.
Mm.
The way that we got around this actually wasn't by the rating scale. The way that we got around it was by changing the data that we passed on to the raters. I don't know how much time I've got to explain this, but if you'd like to know more about this, we are this topic tomorrow. But in short, the machine got very good at rating the central bands, that we could use the machine to do a preliminary rate of data. We then removed a proportion of the central bands, which meant that there were more recordings of students who were at the extreme bands, which meant we could guarantee that there was data for the raters to rate at the extremes.
Okay. My personal question would be, you mentioned the possibility of revising the descriptors. Is that
Yes.
an ongoing research into, would that delve into linguistics or into the possibility of elaborating more accurate language? Or how would that fit with, I mean, how would it play out, basically, this research into the descriptors?
Well, there are a lot of considerations that you have to take when you engage in that process. As I said before, it's expensive to do each of the data points that we used in this research demonstrates someone raised. Say that we wanted to collapse the scale from 12 to 9 bands, because it wouldn't just be a case of removing those intermediates. We would actually have to revise each of the level, which obviously is a huge amount of work, which we wanted to avoid just because of cost. Another issue is that, say you wanted to keep the 13 band scale, an issue with that would be, how do you describe language in 13 steps for any given criteria? We kind of run out of words to describe language, and then you end up with all sorts of difficulties with adverbs and things, and it becomes quite nebulous. So it makes it very hard, which is why I think we decided to go for the intermediates. So in answer to your question, it involves lots and lots of different things. And that depends on how much money you've got, how much time you've got, how many raters you've got, etc. So yeah, it's not easy.
Okay. If there's any other questions, we got about 120 seconds left. Okay. Well, it seems like that's it for this day, and in fact, it's almost time to finish this segment. So thank you very much, William. William, was very interesting, and I should like to announce the next presentation, which will be, well, you can read the thank yous from everybody in the chat line. So next is going to be actually Trevor Breakspear, and it will be very soon in 10 minutes, and it will be an investigation into the provision of pronunciation feedback in an artificial intelligence driven speaking solution. So yes, we concluded for today. Again, thank you for your presentation, William, and I'll see you all soon in 10 minutes.